All right. So just as I said right before this recording started, we're just going to go through a few common probability questions. I think something that's also important to just mention real quick, the importance of probability in the world of data science. Honestly, like when will you be really asked these questions? It's really just during the interview process. I will also admit that it's not one of the more common questions that I get asked, but I have gotten asked like conditional probability questions. Questions of like thinking about permutations and combinations, as well as I don't have an example in here because it's going to be later on, but Bayes' theorem is actually something that I've been asked a bunch because it's kind of like related to statistics. I will say I do get more statistics questions versus probability questions. But yeah, I think it's still important to know just in case they come up. And I think in this slide deck, I have the main groups of questions. So there are like the set questions. There are also permutation combination questions, as well as a little bit of the binomial distribution. This is not a particular question, but I think the binomial distribution, if we have time, because most of the time I don't have this, and if there's not enough time, I actually have a past recording that I will send out as well, just in case. But cool. To get into it, this is, I think, kind of in the order of your labs and lessons. So these questions all come from there. I will talk about what are the equations that are good to remember. Definitely don't have to remember them right now. You can always Google, even during like technical interviews. Most technical interviews allow you to Google things if you're like in front of a computer. But if anything, maybe memorizing them right before an interview that you know is going to be a little bit more mathy, that would be enough. All right, so the first question I have here is on set theory. And the important thing to get out of this is the inclusion-exclusion principle. And that's actually a formula that I will write out in a little bit. But the question to start off is, here we have the question of, we have the supermarket and we want to take note of whether customers have a Visa card or an Amex card or both. So what we're going to do here is, I think one of the simplest techniques that you can use for probability questions, just drawing things out. I think it's very, very underrated. People think that you always have to use like equations to solve a problem, but sometimes it's really simpler to just draw things out. So from here, we're given these probabilities. The probability of having having a Visa is 0.5, having an Amex is 0.4, and having both is 0.25. And then we have all these other probabilities that we have to compute. So to start, for this kind of question, I like to just use a Venn diagram. And when you know when do you know you can use a Venn diagram is usually when you have something that overlaps. If you have some sort of like intersect or like a union, at some point, I think they ask you for like, probably that customer has at least one credit card. Once you have questions that have like the intersect union keywords, that usually indicates that you can use a Venn diagram. So this is a blank Venn diagram for now. You can see that this circle represents Visas, this one represents Amexes, and then the overlap will represent both. So what we're going to do now is we're going to use these numbers and just fill up our Venn diagram. For me, given this data, I actually like to start with the overlap part. So basically this overlap part in the middle will be our 0.25 because both A and B, the probability is 0.25. And as I'm putting this up here, important things to remember about a Venn diagram is that these two circles and this entire rectangle add up to 1. So there is the possibility that some customers have neither card. And so there's a number that can exist outside of these two circles. So we have 0.25 in the middle. What we're going to do is, because I know that we were given 0.4 and 0.5, I think. Yeah, 0.5, 0.4 for the entirety of Visa and the entirety of Amex. Let's just break it down for simplicity's sake, because I think in a Venn diagram, we need to deal with like the overlapping. It gets kind of confusing. So what I like to do is figure out, all right, for the whole of A is going to be 0.5. Because we know that this overlap part is 0.25, this part should be 0.25 because the sum of this, I guess this crescent shape and this, whatever this shape is called, adds up to 0.5. And so therefore, this entire circle ends up being 0.5. And similarly for this side, instead of 0.25, we can just take the circle B should be 0.4. So what's 0.4 minus 0.25? We have 0.15. So we filled up this whole middle section. The last thing we have to do is remember that I said that the part that isn't any one of these circles can also have a probability. And this entire rectangle adds up to 1. To find the probability of neither of the cards, we'll just take a 1 minus the sum of all of this, which I think is 0.65. So this outside part is 0.35. So just like that, we actually have our entire Venn diagram filled. And let's see what these questions are. So the first one is the probability that a selected customer has at least one card. Well, because we have everything filled out here, it actually becomes a lot simpler to solve, right? So at least one card, you can see that all we have to do is add up these numbers, because each of these like crescent moon shaped parts are them owning one of the cards and the middle is both. So the probability of at least one card becomes 0.25 plus 0.25 plus 0.15, which gives us 0.65. Or additionally, you can do 1 minus 0.35, whichever one works. But because this image has everything that adds up to 1, you just have to add the parts that you need. Let's see what's next. Probability that the customer doesn't own any of the mentioned credit cards. And then the last one is only Visa. Cool. All right, so probability that it's neither card. Again, because we have this, we know it's going to be 1 minus 0.65, or because we literally have 0.35 there, there's our answer. And then finally, only Visa. We know here that only Visa would be this crescent moon shaped part here. So we ended at 0.25. So just by taking the time to, annotate a Venn diagram, getting these answers become a lot simpler. But, if you want to do it the formula way, we can do that as well. So for example, what we have to do then is we have to reframe these probabilities into something that we can use our formulas for. So the main formulas that we have here, I think the main ones are, the main one is for this one is the inclusion exclusion principle. So I'll call it the inclusion exclusion principle. And that formula basically says that the probability of A union B is equal to the probability of A plus probability of B minus the probability of A intersect B. This is the inclusion exclusion principle. It can actually be generalized to if you have like more circles overlapping, but I think in most cases, I've never been asked the question outside of within data science interviews having to deal with more than this. So just knowing that the probability of this whole thing is the same as the individual circles minus the overlapping section, that's just a good one to remember. And so we can actually use these formulas here. So at least one card, it's the union. So you can actually pretty much do the same thing here. So A union B is equal to 0.5 plus 0.4 minus 0.25, which brings us back to the same number of 0.65. I think the only, let's see, this one is going to be the same because you just take 1 minus your previous answer. And for only Visa, you can sort of just rearrange this formula. So with this, we're trying to figure out what the probability of A not including B. So I think this is the formal notation. But we can do this by taking probability of A minus the probability of A intersect B. There we go. I think this is kind of I think this is it's derived from this, but yeah, cool. Any questions about this? I think my main thing that I want to get across is just sometimes drawing a picture saves you a lot of time in the long run. All right. So the next thing we're going to talk about, well, it's kind of along the same lines, but permutations and combinations. I think with permutations and combinations, the first thing people get stuck at is when to use which. I will say that it took me a while to also get used to which one to use when. But the main rule of thumb is in permutations, the order matters, and in combinations, the order doesn't matter. So how I remember that is for combinations, I always remember the combinations first for some reason, but I think of combinations as I'm picking things out of a hat all at the same time. It doesn't matter what order it is. And then in terms of permutations, it matters what order I pick things out of the hat. So yeah, questions about that or any like things that were confusing? I think it's just like a matter of getting used to which one is which. But yeah, this is a question that I think most of my forward students have gotten tripped up on a lot. It's, I think, the second part of one of the questions. But basically, this question is about like an iPhone passcode with 4 digits. And on this iPhone, basically someone is trying to get back into their phone, but they don't know their passcode. But you can basically see that there are fingerprints on the digits 2, 7, and 8. And you basically want to figure out what 4-digit combinations can be made with the numbers 2, 7, and 8. And because there's just 3 different numbers, the part that's a little tricky is that one of the numbers has to be repeated at some point in this 4-digit passcode. And so this is part of a bigger question, but here we're just going to find out how many different passcodes can you make, how many different 4-digit passcodes can you make with these 3 different digits. Any questions about this setup? All right. So the way I like to think of it first, I try and simplify the problem first. So I'm just going to assume that the one that is repeated is the digit 2. So first, assume the 2 is repeated. Now with the 2 being repeated, I then think of this as, all right, I imagine my 2s are distinct. This will make sense with a few more. I'm going to give a couple examples, but imagining the 2s to be different 2s, you can basically use factorial formulas. So the way, as an example, and distinct, and 2 distinct 2s. So for example, possible combinations would be, and I'm just going to use 2A and 2B to denote possible combinations. So for example, I have 2, 2, 7, 8. So 2, 2, 7, 8, I'll use 2A, 2B, 7, 8 as one possible combination. And then 2B, 2A, 7, and 8 as another possible combination. And then just as another one, maybe 8, 2A, 2B, and 7. So these are all possible combinations. Because our 2A's and 2B's are distinct, we can treat them as like, just imagine they're different digits. So with this, how many different combinations of, or technically how many different permutations? How many different permutations of these 4 can we get? This is, I think, outlined in one of the lessons, but it's basically factorial 4. If I have 4 distinct objects and I just want to figure out how many ways I can arrange these 4 distinct objects, it is factorial 4. So the number of 4-digit permutations is equal to factorial 4. There we go. So with this, we made an assumption that we don't have anymore, which is that the 2 is that the 2s are distinct. So now we got to account for that. So we saw here that we had 2A and 2B, 2A and 2B here. So technically, these 2 are the same, right? So technically, I don't know why the font is bigger now. These combinations are the same. So just based on this, and you can imagine other scenarios where you have 2A and 2B just flipped around, based on this, you have half the number of combinations. So let me actually deal with this font size because I have slight OCD. At 15, okay. There we go. I'll fix it later. But so each combination or each permutation is being repeated one extra time. And so because of this, we're just going to take factorial 4 and divide it by 2, just to account for the repeating 2's. So taking into account repeats, we're going to have 4 factorial divided by 2. So technically, if we had more repeats, we're actually going to have to divide it by 2 factorial. No, actually, I didn't explain that clearly. So technically, if we had a digit repeated 3 times, we'll divide by 3 factorial. That's just because how many different ways can you arrange 3 things? So technically this shouldn't be just 2, but it's 2 factorial, but 2 factorial is equal to 2 anyways. Does that make sense? Okay. So both of these steps assume that
We lost the sound.
We lost sound for a second, or maybe still.
All good.
Actually, I can hear you now.
That's fine. Yeah, my headphones disconnected for some reason, but no big deal.
Okay,
Alright.
I can hear you now, though.
Okay, so what was I just saying? Right. So if we have the digit 2 being repeated, then this is the number of passcodes that we have. So now the last thing that we have taken into account, what if it is 7 or 8 being repeated? Which we can take the same process to go through and figure out how many combinations there are of like the 7 or the 8 being repeated. But because we know we're going to repeat these steps, we just have to do 3 times that. So if 7 was repeated, we have another 4 factorial divided by 2 combinations. And then same for if 8 was repeated. And instead of combinations, I'm going to say passcodes. All right. So the final answer is actually 4 factorial divided by 2 multiplied by 3. There we go. Any questions about this? Sweet. This is actually one of the more challenging ones. Even me myself, I had to like sit and stare and think about it for a while. But just breaking this up, simplifying it first into like one of the possible scenarios and then working from there, that's what helped me. All right, so the next one is combinations. And remember here in combinations, whereas in permutations, the order of like my 2's and 7's and 8's mattered, in combinations, it doesn't. So the question that we have here is, imagine that you have 6 different consonants and 4 different vowels written on pieces of paper in a bag. So you'll draw 5 letters out of the bag, and then we have to solve these probabilities. What's the probability that you can draw exactly 2 consonants and 3 vowels when drawing 5 letters? And then out of 6 consonants and 4 vowels, how many 2 consonant, 3 vowel words can be formed? So let's break this down again. So it looks like the first thing that they're going to ask about is what's the probability of drawing this combination when drawing 5 letters? So we have to come up with our denominator first. How many possible 5-letter combinations are there? So to start, we'll look at the number of 5-letter combinations. I think this is a little small, so I don't know if this helps. All right, whatever. So the number of 5-letter combinations that you can draw from 10 letters. For the denominator, it doesn't matter how many consonants, how many vowels are in this 5-letter combination. So the number of this is just our combinations formula, which I actually have up here. This formula, I think it's good to remember for your interviews. NCK basically is the number of ways of choosing K out of N. And then this is the permutation formula. I just put it here just for reference. The number of ways that you can permute K things out of N. So I'm just going to use this notation for the rest of this question, but you would just have to plug in numbers to figure it out. So the number of 5-letter combinations we have here is just going to be 10C5, 10 choose 5, I think is the way that people call it. So we have this number of 5-letter combinations that we can get out of pulling from these 6 consonants and 4 vowels. Next, we have to look at the number of ways to choose 2 consonants out of 6 consonants. To choose 2 consonants out of 6. That would just be 6, choose 2. And then finally, number of ways to choose, how many is it? 3 vowels out of 4. That would just be 4, choose 3. So with all of these numbers, you can just put that together to get this probability here. So the probability of A is, we know that our denominator is 10 choose 5. And then when you have your 2 consonants and then your 3 vowels, basically you have to put your 2 consonants and 3 vowels together to form the 5. And all you have to do is just multiply these together. So that will just give you, and you can just plug in the numbers. I think they actually have you write the formula out or code the formula out in the labs. But you just put that together and then you end up with this probability. So the one that's a little bit trickier, I think, is the second part. Out of 6 consonants and 4 vowels, how many words with 2 consonants and 3 vowels can be formed? So let's say we have the letters. All right, so this is the first part. Okay, so let's just assume we have the letters B, C, A, E, and I. So this is one combination of letters. And then let me just make this smaller again. So with this combination, we know that, for example, let's see. If we switch it to like C, B, A, E, and I, these are actually considered the same. All right, let me make this part a little bit bigger. So these are the same. Are considered the same combination. Or the same word. Oh wait, how many words with 2 consonants? Okay, is that considered the same word? Yeah. In our earlier example. There we go. So choosing this, let's say we end up choosing these 5 letters. If we choose these 5 letters, this number of like 4C3 multiplied by 6C2, both of these will be included in that count. Does that make sense? I know I had like a super roundabout way of explaining that, but hold on. Let me see if I can come up with a better way of explaining it. I think I can. All right. So the total number of 2 consonant and 3 vowel words is equal to this times 4C3. And because BCAEI and CBAEI would be considered the same, we're overcounting. That's what I'm trying to do. Or we're undercounting. We're undercounting. Would be considered the same. There we go. So therefore, we have to see for each set of 5 letters, how many ways can we arrange these to create unique words? I think that makes more sense. All right. So what is the number of ways to arrange each 5-letter combination. That would just be the same thing as we were talking about before with permutations. It would just be 5 factorial. So therefore, the total number of words is equal to 6, choose 2, multiplied by 4, choose 3, multiplied by 5 factorial. Cool. Awesome. Any questions about this part? Awesome. All right, so the next question that I have is another example of like how you can simplify a probability question. So this is another one that really trips people up. Let me make this a little bigger for now. But this is doing 2 dice throws. Given that at least one of the dice has come up on a number higher than 4, what is the probability that the sum is 8? And for this, in the labs, they actually have you build up. So they start with a couple questions. First, they actually define events A and B for you. So event A is when either I or J is 5 or 6, because higher than 4. And then event B is when the sum is 8, which is what we're doing here. And conditional probability, and I'll go over those, I'll put those formulas somewhere here in a little bit. But conditional probabilities, and actually I think in the labs, they ask these 2 questions to build up. So what is probability of A intersect B? And then what is the probability of A? And then what we want to calculate is B given A. So given that, given A. So given that I or J is 5 or 6, what is the probability of B? So to put this together real quick into formula, go. The probability of B given A is equal to the probability of, let's see, yeah, B, I think it's intersect, yeah, B intersect A divided by the probability of A. Yeah, actually, let me just put this symbol here so it's easier to see. There we go. So this is the conditional probability formula, which is a good one to remember. Okay, so now that we know what this context is, let's make this smaller so we have more space to work. What I'm going to do here is I'm actually going to insert a table with all of our possible outcomes. And then you'll sort of see why this is easier. So with this table is basically going to represent all our possible dice throws. So we're going to do, let's say, dice 1 and then dice 2. So here we have dice 1 being 1, 2, 3, 4, 5, 6. Oops. And then dice 2 coming up at 1, 2, 3, 4, 5, 6. So how I'm representing this here is each of these squares is going to represent an outcome. So this outcome is going to be 1, 1. This outcome is going to be 6, 6. This is going to be 2, 1, 1, 2, and so on and so forth. So let me just use some colors so that will look a little bit cleaner. Here, this is going to be just saying like what dice has been thrown, and then we're going to fill this all up. We're not going to write out all the numbers, but we know how to read this now. So what they asked us to compute first is the event of I or J being 5 or 6. So first, let's just look at all of the options where you have either dice being 5 or 6. And because we have it set up like a table here, it's actually pretty easy to see. All of this, and let me just fill this in with, I don't know, yellow. And all of these represent outcomes where either dice is a 5 or a 6. And then on top of that, we're going to look for, and yeah, that's event A. So actually, really quickly, probability of A is going to be equal to the number of yellow squares over the total number of squares. So I think this is what, 20? Yeah, 20 divided by 36. All right. So the next part is what is, oh, yeah, that's event A. All right, so event B is when I plus J is equal to 8. So let's think about which dice combinations will give you 8. So here you have, I think 6, 2 will give you 8, 5, 3 will give you 8 as well. Let's see, same here for 3 and 5, and 2 and 6. Other ones that will give you 8, I think 4, 4, and I think that's about it. Yeah, these are the only ones that will give you 8. All right, so the ones that will give you 8 are these 5, but we want to look for A intersect B. So if B is the green squares, I'm going to make these green real quick. Let's see. B are the green squares. Or actually, you know what? I'm not going to use. I got an idea. All right, so this is going to be blue. And then these are going to be green. Because blue and yellow make green. There we go. So what I'm going to put here is yellow is event A, blue is event B, and then green is A intersect B. There we go. Now that we have all of this laid out, we can actually solve our problem. What is the probability of A intersect B? The probability of A intersect B is the number of green squares out of the total number of squares. So actually, let's just do this here. It'll just be 4 out of 36. And then, since we have these two parts together, actually, let me put this separately. Probability of A. I still have this dice. This is going to drive me crazy. Okay. Now that we have this, we can just put it together with our conditional probability formula. So probability of B given A is just going to be, and A intersect B is the same as B intersect A. So it's just going to be 4 divided by 20, which is 1 out of 5. So that's the answer. Questions about this? Sweet. So yeah, I mean, doing it this way, I think is so much easier than doing it the formulaic way, especially when you have wording that can come up a little bit ambiguous. Like, for example, they highlight that, you know, you got to keep an eye on like either or. That part can be a little bit tricky because I think some people will take like the, if dice 1 is 5 out of 6, and then this part, and then they have to deal with this overlapping section here. I know that's something that people do. So yeah, just to really quickly also go over how you would do this formulaically, just so that we have that here. Let me just make this a little bit smaller. Oops. Bear with me a little bit. Why isn't they letting me resize? That's probably why. All right, this is not gonna look pretty. But here, I have a bunch of the solutions over here. And I'm just going to paste that in a text box here, just so you can see how you would solve this formulaically. Cool. So ways that you can break this problem apart, just to talk about some of the traditional ways of going about this. Size of the sample space, we have 6 times 6. Probability of A intersect B, we figured this out from here. The part that was mainly difficult for people to figure out, I think, was calculating this 20 out of 36. So this part is hard because you are actually using the inclusion-exclusion principle here, which I think some people get tripped up over. So what this equation is made up of is 1/3 is the probability of your first dice being a 5 of 6. This second 1/3 is your second dice being a 5 or a 6, and then you have to minus this overlap, and that's how you get 20 out of 36. But the rest of this problem works out the same way as we did before. So this will be here just for you all to have. Cool. All right. There is about 15 minutes left. Before I move on and finish this up. Has anyone thought of like any other questions for this office hours that I don't want to take up this? I don't want this to take up all the time if not needed. All right, awesome. So this was another question that people got tripped up over, which is, let's see, let's go through. So let's say you have a 2-card hand drawn from a standard playing deck. What is the probability of drawing 2 aces given that we know one of the cards is an ace? And so I actually think that this is the solution right here. And I guess we can break this down together. So if you know that one of the cards is an ace, what they're doing here is they are laying it out in terms of the conditional probability formula. So given that one of the cards is an ace, what is the probability that both are aces? And then you can basically move things around, manipulate the equation such that it looks like this. I think getting from here to here is slightly harder. So let me get a text box here. All right. So finding the probability that both cards are aces, you're actually using combinations. So this part of finding the probability of both our aces comes from the combination formula. Getting the probability that neither is an ace is actually very similar. It's just 1 minus the combinations formula. Result from combinations formula. So this part where you have 1 minus 48 choose 2 divided by 52 choose 2, you're actually looking at 1 minus all of the other 2 card combinations that are not aces. It's actually a little bit easier to do this versus summing up all the probabilities of having both being aces and 1 ace in whatever 2 card combination, if that makes sense. So putting that together, that's how you end up at 1 over 33. The other question here is, what's the probability of drawing 2 aces knowing that one of the cards is the ace of spades? This one's a little bit simpler, maybe harder to think about for some people as well. But if you know that one of the cards is an ace of spades, basically you have that card set. Therefore, the probability of the other card of both cards being an ace is the same card that you're drawing another ace out of the remaining cards in the deck, which is how you end up at 3 out of 51. But I think most people got tripped up here rather than here. Thoughts, questions?
Yeah, you mind going over the top part again?
Oh, yes, absolutely. I think I like kind of skimmed over it a little bit. Okay, so let's just break this out a little bit more. So this first part of both our aces, it's number of ways of choosing, let's see, choosing 2 aces out of 4 aces. That's where you get the 4 choose 2, divided by the number of ways of choosing 2 cards. So that's how you get to 4 choose 2 divided by 52 choose 2. You can put that here. 4 choose 2 divided by 52 choose 2. And so this second part of finding the probability that neither is an ace is we're looking at 1 minus choosing 2 non-aces, number of ways of choosing 2 non-aces out of 52 cards. Yeah. There we go. So it's actually more probability, but yeah, the number of ways of choosing 2 non-aces out of 52 cards. And because non-aces, you have 48 of them. So number of ways of choosing 2 cards out of 48 divided by 50 choose 2. 52 choose 2. So that's where you get 48 choose 2. Does that help? Yeah, it takes a lot of practice. I will say I took like 3 different probability and statistics classes in college alone. And I feel like that is a big reason why I'm used to it, because I've just done a lot of probability questions. I think something like probability, it really just takes practice, unfortunately. But for data science, not super common in interviews, but might come up. So just good to have like at least ways of thinking in your back pocket. Awesome. Anything to clarify here? Sweet. Well, the last thing I wanted to talk about was the binomial distribution. I just think it's a really, really neat formula to just be aware of. It is, I think the binomial distribution comes in like section, like topic 12 or 13 in the lessons, I think, if I'm not wrong, which has a really neat formula that actually kind of ties together the combinations formula as well.
Isn't it a little bit easy just to multiply 2 non-aces than just doing choose in the previous problem?
Say that again?
Is it a little bit easier for the like for 48 choose 2 and 52 choose 2 divided? Isn't it a little bit easier to do just 48 out of 52 times 47 out of 51?
That's actually a really good point. Yeah. Because if you were to do this division, that will evaluate.
I'm just logically.
Yeah.
You have 48 non-aces out of 52 cards, and then one non-ace is gone, so you have 47 out of 51.
Yeah, actually, yeah. That's a good point.
And for the numerator also, it's possible
Mm-hmm.
to go
Yeah.
similarly.
Yeah, for sure. Because once you do this, the denominators kind of cancel out anyways. And then, yeah, you end up with the same result. Definitely. Yeah, I think there's like another subset of people that think of probability as, or any of these like permutation combination questions as like, when you want to do, I think it's more on the side of like permutation, but you end up doing like 52 times 51 going backwards and then dividing it by it going ascending. I don't know if that.
No, I mean just logically. I understand that mathematically it would be the same, but logically you can also do that.
For sure,
Because
yeah.
in the same for both aces, you have 4 aces, so it's 4 out of 52 times 3 out of 51.
3 out of 51. Mm-hmm.
For the numerator.
Definitely, yeah. I think the moral of the story here is that there are multiple ways of solving probability questions depending on which angle you're looking at it first. So yeah, definitely that way. I think whichever way just comes to you first, just go off with that. Awesome. Thanks so much, Jean. Yeah, so just to round off, to just break down the binomial distribution, an example question that you get, and I think they have you like code out a couple examples of this at some point, but they give you the formula and you pretty much plug it in, but I think it's important to figure out like where this formula comes from. So a quick example, let's just say that you have the probability of 0.8 of making a shot. What is the probability that you make 2 out of 3 shots? So with the binomial distribution, when you know that you got to use the binomial distribution, it is characterized by 2 things. One, you have a certain number of trials, and this is the n equals 3 part. And this is just the mathematical notation for expressing a distribution, not a big deal, if this doesn't make sense. But basically, the 2 parts of a binomial distribution is the number of times that you're doing a trial, and in this case 1 trial is 1 shot, and you know here that you're going to make 3 shots and you want to find out the probability of you making 2 out of 3 shots. And then the other component of a binomial distribution is the probability of success in 1 shot. So here we're trying to figure out what's the probability that you make 2 out of 3 shots. I think one common misconception is that you will just take what 0.8 times 0.8 for 2 successes, but it's a little bit more complicated than that because you have to consider the order in which you're making your shots. So I have this from the last time I did this, but basically making 2 out of 3 shots, you can do this 3 different ways. Or in other words, you can do this in 3 choose 2 different ways. I have V's and X's. V basically means, I guess, a tick, and X for a cross. So let's say you make the first 2 and you miss the third. You make the first and third, miss the second, miss the first, make the second 2. These are the 3 different ways that you can make 2 out of 3 of your shots. So with that, you already have 3 different kinds, 3 different, at some point you're gonna have to multiply your probability by 3. Or by 3 choose 2, more technically speaking. So now that you know that you have 3 different ways to make 2 out of 3 shots, we got to find out the probabilities of these, which is pretty straightforward because we're given the probability of making a shot. So making a shot is 0.8, not making a shot is 0.2. So the probabilities put together for one combination of making 2 out of 3 shots is just 0.8 times 0.8 times 0.2. So putting this together with your 3 choose 2, that's how you end up with your final answer. That is basically how I would break down this equation, because you are taking the number of successes and that probability associated with that, and the number of ways that you can get however many successes out of the number of trials. So I think that's just some useful intuition to have when you're dealing with binomial distribution. But cool. Any thoughts, questions? Awesome. Well, that's pretty much all I had to share for today. Thank you for coming to office hours. Feel free to reach out to me on Slack if you have any questions. I have a math background, so I like dealing with numbers a lot. I don't know what else I can add. But yeah, any questions, feel free to reach out to me. I know Joel is out for the rest of the week, I think. So yeah, happy to help with whatever y'all are doing.
Thanks a
Cool.
lot.
You're welcome. Well, have a good night, you guys, and I will see you on Slack.
Thank you.
Bye.